Well, hello and welcome to another installment of linear algebra. In our last video, we had talked about, I don't know, what did we talk about? Oh, this is the same video. I get it. Okay. Well, we talked about some properties of sort of like what we want out of an ideal, uh, what we wanted out of an ideal determinant. So what we're going to do is we're going to sort of like take a look at some of these properties and like figure out what this means in terms of ramifications for the determinant of a matrix, and we'll sort of like flesh them out a little bit. And so we'll talk about like, we'll just call it maybe further properties of the determinant. Of the determinant. And let's take a look at sort of like what some of these are. So, okay, we had this idea that there was this geometric motivation for figuring out the determinant, and basically what we want to say is that like we don't, that motivation kind of goes away in different vector spaces, but the sort of basic properties of the determinant remain the same. And so we're just going to sort of like look at some of the basic properties, and for the most part we'll stick to real matrices with real entries. It works for complex entries as well. It also works for matrices over arbitrary fields, so matrices of functions or matrices of things that are measured sort of differently than how we measure real numbers, but that's sort of like a little bit farther. So we're going to use some properties that we had talked about, right? And we're going to sort of see how we can take these basic properties that we talked about in the previous video and sort of leverage them to talk about some specific properties of our determinant. So just as sort of like a recap, we had linear in each column, right? So the determinant is linear in each column. And basically the sort of way that we could write that is if you have the determinant of like v1, v2, and then we have some like linear combination in a spot. So I've got alpha uk plus beta vk, if this is sort of in the k spot, and then I got some more vectors in this bundle. The determinant of like all of these vectors smooshed together, and again this is like a matrix. Well, we can split it out into alpha times the determinant of like v1, v1, a bunch of other ones. And then this one is just going to have uk in it, in the k spot, and then it's got vn. And then to that I'm going to add beta, and then I've got the determinant of the one with vk in it. And what we can see out of this, and again, this is what we had talked about before, but we have some sort of like linear combination of inputs of columns, remember? So that's why we're saying it's linear in each column. If I have like a linear combination of an input in a column, that's that linear combination of outputs. So that's what we mean when we say it's linear. And that's what we mean by it being linear in each column. Sorry, my video's like glitching out on me or something. Okay, so that was the basic property we talked about before. The second basic property we said was that like it's antisymmetric, right? It is antisymmetric. Basically, like if you switch, well, the fancy word for switch is interchange. If you interchange two columns, like the determinant changes sign. That's sort of like what we mean when we talk about antisymmetric functions. And then we've got this last one that was like, well, we called this normalization. Basically, we said like the determinant of the identity matrix is 1. So again, we sort of like talked about this before. We kind of wrapped up this linear argument into 1. Yeah, so let's take these 3 properties completely define what we want out of a determinant. They sort of completely define the determinant. And what's neat is we can sort of, from just these 3, we can write some really neat sort of ramifications of this. So I'm going to call this proposition, just crossed a T and an I there. So proposition 3.1. And this is just going to be sort of like the properties of determinant. Okay, so what I want to sort of distinguish in these properties and the properties we began with, these basic properties, 1, 2, and 3, were sort of like what we wanted out of an ideal determinant. And the properties we're going to list out here, there's 4 of them, are sort of like they're consequences of the ideal properties that we have. And we'll make these letters so that we don't sort of cross-mogenate what we have. So we're going to talk about like, okay, these are only for a square matrix. So for a square matrix. Matrix A, the following hold. Properties hold. All right, well, the first one, and this is going to get pretty neat, like right off the bat. If A has a 0 column, det A is 0. That's neat. We'll prove these in just a second. These aren't hard to prove. If A has 2 equal columns, oh geez, guess what? The determinant is also 0. 3, or C. If 1 column of A is a multiple of another, well then, I bet you can guess that the determinant of A is 0, and then this is sort of the big one. If the columns of A are linearly dependent, think about what that means. That means A is not invertible. Ooh, that's important. Then I'll bet you can guess the determinant is 0. So we have like some really interesting properties here, and they're going to be really helpful in terms of like hopefully they sort of show some of the value of the determinant already, because we can sort of see that a 0 determinant is going to tell us a lot of things that we might need to know about our matrix and about the sort of vectors that are in that matrix. A is really neat. A follows almost immediately from linearity. And sort of what I mean by that is if you have like D, V1, V2, sort of like, and then you have some VK, well, we'll just say then you've got a 0 column in there, and then a couple others, and then like Vn. Well, that's really like the determinant of V1, V2. It's 0 times some vector, which we'll say maybe this is in the kth row. And I can pick any vector that I want, 0 times Vk, because that zeroes out the vector. And by linearity, I can pull this 0 out front, which is 0 times the determinant of like something. Well, 0 times anything is 0. So that's a pretty quick argument to make, that if you've got a 0 column, you can consider that 0 as a scalar multiple of really any vector that you want. Because we can pull scalars out by linearity, that's going to zero out the whole determinant. Sure. So B actually follows from anti-symmetry. And what we mean by that is like, okay, so we have 2 equal columns. So we'll say like, without loss of generality, which basically means we can pick any 2 that we want. So I'm going to say that like Vj and Vk are equal. Okay, well then what that tells me is that like the determinant of V1, Vj, Vk, and this determinant, right? It's like, maybe I'll just write them out here. Vk, Vn. So this determinant, if I pull it, if I switch these two are the same, right? But if I switch them according to my property, I have to say Vj, Vk, N. Well, this determinant and this determinant should be the same number. Oops, I switched them. Okay. And what we know about anti-symmetry is that when you switch these 2 columns, you have to pull out this negative. But because Vj and Vk are the same, this actual number, right, because the determinant is just a number, this actual number part and this actual number part are the same. So if that determinant is some number, we'll say like y, the equation that I've come up with is that, well, y equals negative y by anti-symmetry, and, well, the only number that that's true for is 0. So if this anti-symmetry is true, and you have 2 equal columns, when you swap those columns, you pull a negative out, but you don't change the numerical value of the determinant. And the only way that you can do that is if D is 0. So that's sort of our proof that of property B, if there's 2 equal columns in your matrix, the determinant is 0. Okay, let's take a look at a couple more things. All right, so, well, like statement 3, if one column is a multiple of another, that follows like straight from linearity and this anti-symmetry argument. You would just like multiply by a scalar and do a swap, and you'd get the same thing. That's not really super interesting. But what is really interesting is, let's take a look at D, right? And D said the columns of A are, if the columns of A are linearly dependent, that if the columns are linearly dependent, then A is not invertible, but that's okay. Then the determinant is 0. That's really interesting. And so let's take a look. We'll sort of suppose V1 is a linear combination of the other vectors. Of, say, like BI, and then I is going to start at 2 to n. So what we're going to say is if the columns of A are linearly dependent, then one of the vectors is a linear combination of the other. We're just going to start and say it's V1, and then we could sort of generalize it a little later. Well, that means, right, this means that V1 is equal to maybe alpha 2 V2 plus alpha 3 v3 plus, I don't know, a bunch more, plus alpha n vn, right? I can represent it as a linear combination of these guys. And if I wanted to write that in summation notation, I could write k equals 2. I want to start it at 2 to n of like alpha k vk. That's equal to v1, right? Okay, so then, right, let's consider the determinant. The determinant of v1, vn, I've got all these vectors in here. Well, that's really equal to the determinant. We said v1 is just this sum, right? So it's sum k equals 2 to n of like alpha k vk. That's my first vector, that's v1. And then I've got like v2, v3, all the way to vn. Well, like by linearity, I can pull this out, and I can pull out all of these vectors. And so what I can say is I can say k equals 2 times I'm going to write k equals n of alpha k, right? And then what I'm going to have left is the determinant of like vk is going to go into this spot, v2, v3, v4, all the way to vn. And this k is indexed, right? So there's actually a bunch of determinants in this sum, right? There's the determinant of like, well, v2, v2. So it's like alpha 2, v2, v2. And then the next one in the sum is like alpha 3, v3, v3. And what you'll notice is that like, well, guess what? Every one of these in the index sum, vk shows up here, and it'll show up again. So this is like, in the first term, this is v2, well, and this is v2. And because we have equal columns, that's 0. And then the second term in the sum, when my index shifts over to k equals 3, this will be v3. Well, guess what? v3 shows up again, and v4 shows up again, and v5 shows up again. So this is equal to 0 by my duplicate columns argument. So this is equal to 0 for all, like, well, I'm not going to say for all, but for like k equals 2 all the way to n. So all of these are 0, so the determinant of the whole thing is 0. Neat. That only happens if you have v1 as your linearly dependent vector, but you can switch any two columns that you want, and you pull out a negative sign, then you could make the same argument again, and you would have vk in this first column. So that sort of proves the 4 corollaries that we have with the properties of determinant that we're going to use a bunch. Thanks for watching, and I think we'll probably call it a day, because this is a lot, and then we'll come back tomorrow and do some more stuff. Neat.